Hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be learning how 3-wire split-phase electricity supplies work to get 120 and 240 volts. We'll look at how the electricity gets from the power station over to the property and then how it's connected around the property and each of the main components. Now this system is used in North America, so we'll be using their terminology and color coding. If you're from outside this region, then you can still follow along, but your electrical system will work differently. We've covered that in a separate video, do check that out, links are in the video description down below. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So electricity is generated at the power station, which is usually located far away. The power station generates AC alternating current and is connected to a step-up transformer. This transformer increases the voltage to reduce losses and is connected to the grid. The grid carries high voltage electricity over long distances over to the towns and cities. Once it reaches the towns and cities, it will enter a step-down transformer, which will decrease the voltage to a safer level. From here, it will be distributed locally into smaller circuits on different streets or groups of properties. Connected to these distribution cables will be smaller transformers, usually pole-mounted, which again reduce the voltage down even further to a level safe enough for residential use. On the property will be an electricity meter, which will quantify how much electricity has been used, and the electricity company will use this to invoice the property. The transformer will be connected to the electricity meter by some cables which will either run above ground or underground. These cables will be 2 hot wires and a neutral wire. Inside the transformer we have 2 coils of wire. The primary coil is connected to the power station and the second coil will be connected to the property. The 2 hot wires are connected to each end of the secondary coil and the neutral is connected to the center of the coil. Now don't worry about that too much for now, we're going to look at this again later in the video to understand it. So if we zoom into the property, we find a main service panel which is sometimes called a load center or breaker box. If we remove the cover and look inside, we first find the main breaker. This is usually at the top of the panel, but it might be at the bottom. The 2 hot wires from the electricity meter will connect directly to the lugs on the main breaker. Coming out of the main breaker will be 2 main bus bars. These are basically exposed metal sheets which carry electricity to the circuit breakers. Notice I've shown the current flowing backwards and forwards. That's because this is AC or alternating current. These bus bars as well as the lugs are not insulated, they are live or hot. The main breaker can be manually flipped to cut the power to everything downstream of the main breaker. The main breaker will also provide overcurrent protection to the property. It is rated to handle a certain amount of electrical current passing through it, typically between 100 and 200 amps. If this value is exceeded, then it will trip automatically to try and protect the property and its electrical circuits. Inside the panel, we also have a neutral and ground bus bar. This is basically a strip of metal with lots of holes and screws in it. The neutral and ground wires will sit in the holes and the screws will lock them in place. In this example, we have a block on either side of the panel. As this is a main panel, the 2 bus bars can be joined together, so we have a connector bar between them. That way we have a shared neutral ground bus bar. Sub-panels must have their bars separated, but that's a topic for a separate video. From the electricity meter, we will have the neutral wire connected to the lug on the top of the neutral ground bar. Notice the green screw. This is bonding the neutral bar to the metal casing of the service panel. The purpose of the neutral bar is to return the used electricity back to the transformer. It does actually get a little bit more advanced than that, but we're going to look at that in a more advanced complex video. This is just covering the basics. So the 2 hot wires will provide the electricity, and once it is used, it will return to the transformer via the neutral bar. It is still AC alternating current, but to make it easier to visualize, I've only animated the current flowing in one direction so you can see the path it will take. Now if we were to take our multimeter and connect one lead to the bus bar and the other lead to the neutral bar, we would get a reading of around 120 volts. If you don't already have a multimeter, then I highly encourage you to get one for your toolkit. It's essential for any electrical testing and fault finding. Links down below for which one to get and from where. If we connect the multimeter leads to the other bus bar and the neutral bar, we would again get a reading of around 120 volts. But if we connect the multimeter leads to the 2 bus bars, then we get a reading of double that at around 240 volts. So why is that? What's happening here? So when we look at how the transformer is connected to the main panel, we have the two hot bus bars connected to either end of the secondary coil in the transformer, and then we take the neutral bus bar connected to the center of the secondary coil. So basically, when we connect across the bus bar and the neutral bar, we're only using half of the coil. So we are only picking up half the electrical voltage the transformer can provide, so that way we get 120 volts. When we connect to the two bus bars, we're connecting to the full length of the coil, so we're picking up the full voltage which the transformer can provide. Therefore, we get 240 volts. If you want to learn how transformers work, then check out our video on transformer basics, links for that down in the video description below. Now coming back to the panel, connected to the bus bar, we'll have our circuit breakers. These will look something like this with this black plastic casing and a toggle switch on top. The circuit breaker controls the flow of electricity into individual circuits in the property. It can be manually tripped to cut the power, but it also has two important features. The first feature is overload protection. The circuit breaker is rated to handle a set amount of electrical current. When appliances or lights are connected to the circuit, they will each increase the current in the circuit. If too many things are plugged in and turned on, then eventually the current will be more than the breaker can handle, and the breaker will automatically trip to cut the power off to the circuit and protect the property. The second feature is short circuit protection. When the hot and neutral come into direct contact with each other, the current will dramatically increase almost instantly. When this occurs, it creates a magnetic field which will trip the breaker and cut the power automatically. Let's have a look at how the circuit breaker is connected to the electrical circuit. In this example, we will connect to a simple light fitting which is controlled by a switch. We take the hot wire from the circuit breaker and run this to the switch. We then run another wire from the switch and over to the light fitting. From the light fitting, we have a neutral wire which carries the return current back to the neutral bus bar. We take the ground wire from the metal casing of the ceiling box and the switch, and we also join this to the neutral bus bar, as in this case it's shared. The purpose of the hot wire is to carry the electrical current over to the light fitting. The purpose of the neutral wire is to carry the used electrical current back to the main panel and then back to the transformer. The purpose of the ground wire is to provide protection for a fault current. If, for example, the hot wire came loose and touched the metal casing of the light fitting, the ground wire provides a low resistance path back to the panel. Without this path, electricity could flow through you if you touch the metal box. As the current flows through the ground wire, it will increase the current and that will trip the breaker automatically. So the electricity flows through the hot wire, through the main breaker, down the main bus bar, and into the circuit breaker. From there, it flows along the hot wire, across the switch and light, then back along the neutral wire and into the neutral bus bar, along the neutral bus bar wire, and back to the transformer. I've animated this using AC alternating current, but to make it easier to understand the path, I've shown it flowing in a single direction now. We've covered lighting circuits in detail in a separate video. Do check that out, links in the video description below. Okay, so what else might we find here? Well, we might find a double pole circuit breaker, which will let us connect to both bus bars to get 240 volts, which we can use to power larger appliances like dryers, ranges, and air conditioning units. If we look at the dryer circuit example, we run the red hot wire from the circuit breaker, which is connected to the main bus bar number 2, and we run this to the receptacle. Then we run our black hot wire from the other terminal of the circuit breaker, which is connected to bus bar 1, and we connect that to the receptacle also. In this case, we have the neutral wire connected between the neutral bus bar and the receptacle, which will allow us to get either 120 or 240 volts from the outlet. Then we have a ground wire to provide a safe route for any fault current. Now we can either connect across the two hot wires for our 240 volt connection, or between the hot wire and the neutral wire to get 120 volt connection. We'll also very likely find a GFCI circuit breaker, which stands for Ground Fault Circuit Interrupter. This will look something like this, and depending on the model you buy, you will usually have a pigtail neutral wire connected to it. GFCIs are required on certain circuits where outlets are used for places like kitchens, bathrooms, hot tubs, etc. You should check with the National Electric Code for exact details. The GFCI breaker has both the hot and the neutral flowing through it. This way it can measure the current flowing through both wires and ensure they are equal. If we took a standard outlet, we would take our hot wire from the breaker and connect this to the outlet terminal. Then we take the neutral wire and run this back directly to the circuit breaker to a specific neutral terminal. We then connect the pigtail wire into the neutral bus bar. This will provide the return path. And of course, we run the ground wire from the outlet back to the neutral ground bar. If we look at this example, the current is flowing normally until the guy sticks a screwdriver into the socket. The electricity then flows through him instead of the neutral wire. The GFCI is measuring the current in the two wires and notices that these are not equal. It then automatically trips the breaker to cut the power and save the man's life. We might also come across an AFCI circuit breaker. This stands for Arc Fault Circuit Interrupter. These are required for circuits feeding bedrooms, hallways, kitchens, etc. Again, check with the National Electric Code for exact details. AFCIs work also by being connected to both the hot and neutral wires. Inside this circuit breaker is a circuit board which is measuring the circuit and monitoring for patterns which indicate an arc fault is occurring. These are installed pretty much identically to how we saw the GFCI breaker. Under normal conditions, the current flows through the hot, back through the neutral into the breaker, then through the pigtail and back through the neutral bar. But if, for example, a screw was accidentally inserted very close to the cable and removed the insulation to expose the copper wires, the electricity could now potentially jump across or arc from the hot wire and into the neutral. The arc is incredibly hot and causes most residential electrical fires. As the arc occurs, it creates a unique signal in the electrical cable. The circuit breaker can detect this and will automatically trip to cut the power. Connected to the neutral ground bar will be a thick, uninsulated copper wire which runs out of the bottom of the panel and off to the ground rod, which is pushed into the earth near the property. Under normal circumstances, no electrical current will flow through this wire. Its purpose is to dissipate high static voltages from things like lightning. This way, the electrical systems and equipment is protected from damage. Additionally, we'll also find a bonding wire to metal pipework in the property. This is to provide a safe route for electricity to flow should a hot wire come into contact with a metal pipe, and this way it will prevent a person being electrocuted if they were to touch the pipework. Okay guys, that's it for this video, but if you want to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, as well as theengineeringmindset.com.